Chapter 4 covers energy and matter. So we're going to talk about how energy works in chemical systems. We'll talk a little bit more about the states of matter, and we'll look over some energy curves and heating and cooling curves as well. So what is energy? Energy is the capacity to do work. It's just the ability for something to do something. There are two types of energy. The first is kinetic energy, and that's the energy of motion. So when anything is moving, it has kinetic energy. Potential energy is stored energy. So this is energy that can potentially turn into the energy of movement, but it's stored at the moment. So it's not currently being used, but it has the potential to be used. Energy is neither created or destroyed. So you can't make more energy. The only thing that you can do is convert it. So you can change it from potential to kinetic or kinetic to potential, but you cannot create or destroy energy. We have a finite system in the universe. There's only so much energy available, and so we can't make more and we can't destroy it. We can only change it from one form to another. So if you look at this figure, you're going to see how energy can change. So if you take a ball and you throw it up in the air and then it comes back down and it bounces, okay, so what's happening is here, as you throw the ball, kinetic energy moves into the ball. Now the ball is moving. So as the ball moves, it has kinetic energy. When it gets to the top point of its arc, all of the kinetic energy has now been converted into potential energy. So at the top of the arc, the ball is no longer moving, right? So right here, right when you get to the very top, ball isn't moving. All energy has now been turned into potential energy. The ball is now going to start to fall back down toward the earth, and as it does, that potential energy gets turned back into the energy of movement. So the ball starts moving again, and so it's using kinetic energy to move. And then it hits the ground, transfers some of that energy into the ground, and bounces back up. So as things are moving and changing, they are both using and storing energy. The units of energy that we use in science are calories, and calories equal the amount of energy needed to raise 1 gram of water 1 degree Celsius. So if you take a gram of water, you have to use 1 calorie to heat it up 1 degree Celsius. Now the calories that I'm talking about are different from the calories that you find in food in one very specific way. The calories that I'm talking about, 1 gram of water raised 1 degree Celsius, there's 1,000 of those in 1 kilocalorie. And 1 kilocalorie is actually the calories that you see here on your nutrition facts on your packages of food. So like this here, it says it's 200 calories per serving. Okay, in reality, this is 200,000 calories, the calories that I'm talking about that we use in science. Okay, so the calories that are in your food are actually kilocalories. Another type of energy unit that we use are called joules, and 1 calorie is equal to 4.184 joules. So you'll see both of these, joules and calories, on your exams, quizzes, in lab, etc. So we did already go over the states of matter, but let's take another look at it just to remember what they were. So if you remember, we have the 3 states of matter: solid, liquid, and gas. And if you remember, there is a 4th state of matter. It's called plasma, but we don't need to worry about that for our purposes. So again, solids, particles are close together, highly organized into a pattern. The atoms themselves have low amounts of energy, and they are highly organized. It keeps its shape, so if you put it into a container, it doesn't change shape. Okay, Liquids are going to be somewhere in between a gas and a solid. The particles are spaced out slightly. There's disorganization, but not nearly as much as what you would see in a gas. And they have medium amounts of energy. So they can move around a little bit. They vibrate some. They move past each other, but they are touching each other. The atoms are, the molecules are. In a gas, there are large spaces in between the particles, so that you see that here there's lots of space in between the oxygen and nitrogen that's in this particular picture. The molecules are highly disorganized, so it's chaos. There's no rhyme or reason to where you find the molecules in space, and they are high energy. They vibrate, they move around really fast in space, they bump into each other, they bounce off of each other. Gases are moving around really quickly. Why does that matter? Well, we're going to be seeing a lot of different types of states of matter in lab, so that's kind of important because you need to be able to identify these different states of matter in lab. And also we'll be using different states of matter in our labs. You'll be using liquids, you'll be using solids, you'll even be using gases as well. So this just shows you basically the differences between these three states of matter: the shape and volume, the arrangement of particles, density, particle movement, interaction between particles. Okay, so in a gas, it fills up a container. It is disorganized and random. The density is low. So if you remember, we talked about density before. That's grams per milliliter. This is low density. So there's not a lot of matter in a given volume. The particles move really fast and they don't really interact between each other. So they might bounce off each other, but they're not really attracted to one another, the particles. In a liquid, it has a fixed volume that takes the shape of the container that it's in. The particles are randomly arranged, but they are close together. The density is high, so there's lots of particles per area of volume. The particle movement is moderate, so they do move around, but not nearly as fast as what you would see in a gas. And the interaction between particles is strong. They're close enough to each other that there can be attractive forces in between the particles that keep them stuck together. In a solid, we have a defined shape and volume, a fixed arrangement of close particles, usually in some sort of pattern or array. Density is high. The particles move and vibrate very slowly, and the interactions between the particles are very strong, so they like to stick together, basically. Now, how do these things stick together? Well, generally between molecules, we have something called intermolecular forces. This is just forces between molecules, basically how they can stick together. There's three kinds: London dispersion forces, dipole-dipole interactions, and hydrogen bonding. London dispersion forces are the weakest of these intermolecular forces. So if there are London dispersion forces occurring between molecules, the molecules are held together very loosely. This is exhibited by basically all molecules. Any molecule out there in the world can have London dispersion forces. Dipole-dipole forces are moderate in strength, and they only occur in molecules that have a net dipole. So when we looked before at how molecules are set up in covalent bonding, we looked at dipoles, and that's sort of where you see the slight positive and slight negative charges on molecules. So like in water or other types of molecules, we see a dipole moment where you have slight charges on the molecules. Now, the last one is called hydrogen bonding, and this is going to be our most important one, the one that we're going to talk about the most. And this is the strongest of all of the intermolecular forces, and it occurs between a hydrogen and either an oxygen, a nitrogen, or a fluorine. So you have to have one of those molecules, or you have to have a hydrogen and then one of those other three molecules bonded to the hydrogen to create a hydrogen bond. Okay, we see this in water. It's an important force that is occurring in water and what gives water a lot of its special characteristics. But it is the strongest of all of these forces. It's basically what holds water together, what makes water stick to itself. Okay, so let's look at this a little bit more. London dispersion forces are between molecules. Generally speaking, you have some slight positive and slight negative charges that occur on a molecule, even if it doesn't really have like a dipole moment, just because sometimes the electrons are over here and sometimes they're over here and maybe sometimes they're over here. So there might be a buildup of electrons in a particular space at any given moment, and so there could be a slight charge on particular parts of the molecule at any given moment, and these can change over within nanoseconds. Where these charges occur can change. If there are slight charges, and I'm talking super duper tiny slight charges that you're seeing on a molecule, the slight charges here would be in the slight negative charges would be attracted to the slight positive charges on another molecule, and that could hold these two molecules together, basically attracting them. Remember, opposites attract. In a dipole-dipole interaction, we're seeing something where you have a slight positive charge on one end of the molecule and a slight negative charge on the other end of the molecule, and so the slight positive and the slight negative charges are attracted to each other, and then that causes these molecules to be stuck together. It's very, very similar to the next one, which is hydrogen bonding. Hydrogen bonding is basically a very specific type of dipole-dipole bond, and it's the strongest of the intermolecular forces that we're going to find. So in hydrogen bonding, you have a hydrogen atom that is bonded to either an oxygen, a nitrogen, or a fluorine atom. And then it is electrostatically attracted to another oxygen, nitrogen, or fluorine atom in another molecule. So hydrogen is bonded to oxygen in this molecule, which is water. So this can have hydrogen bonding because it has the hydrogen-oxygen bond. If this was a nitrogen or a fluorine, it would work the same way. So because we have a hydrogen bonded to an oxygen, this can hydrogen bond. The hydrogen bond is between the two molecules. In this case, we have the hydrogen here on this molecule, hydrogen bonding to the oxygen on the other molecule. This happens because of dipoles, because hydrogen here is slightly positive, the oxygen here is slightly negative, so we get an interaction here. These are attracted to each other, and so they stick together. Boiling point and melting point of substances is important to know because it kind of can tell you what you're going to see at room temperature. So boiling point is a temperature at which a liquid is converted into a gas. Remember, we're always measuring this in Celsius or Kelvin. We never measure in Fahrenheit, not in science. And the melting point is the temperature at which a solid is converted into a liquid. These numbers are going to be very specific to the molecule that you're talking about. So the boiling point and melting point for water is different than the boiling point and melting point for carbon dioxide. They're going to have different numbers. This is very specific to the type of compound that you're looking at. Specific heat is the ability of a material to absorb heat. So basically, can a material hold on to heat readily, or does it resist changing temperature? Does it resist holding on to heat? Does it dissipate the heat and the heat does not stay in the material? This is basically what we're talking about here. Different types of materials will have different specific heat. So some things like to hold on to temperature or hold on to heat and don't change temperature very readily. Other things do. Specific heat has a very special equation that you use. Specific heat equals heat divided by mass times time. The larger the specific heat, so the bigger this number is, the greater the capacity to absorb heat. It takes more heat to change the temperature when this number is high. Water has a high specific heat. Why does it have a high specific heat? Because of this here, hydrogen bonding. Hydrogen bonding in water is so important and creates all sorts of different types of cool things about water. And we'll talk a little bit about that, but you may see more of that in other science classes as well. Water is just super cool. So you may need to calculate specific heat, given heat and mass and time. So you may, on an exam, need to know how to do this and then understand what your answer means. Does your answer mean that you have a high specific heat and therefore it takes more heat to change the temperature, or is it low specific heat? Does it only take a little tiny bit of heat to change the temperature? Right? You need to be able to understand the difference between high and low specific heat. Energy and phase changes. So you can change from one state or phase of matter to another, and there are very specific words that we use to convey changing from one to another. So if you're changing from a solid to a liquid, that is called melting. If you're changing from a liquid to a solid, that's freezing. There's an I missing there. Anyway, if you're changing from a liquid to a gas, that's evaporating. From a gas to a liquid is condensing. If you go straight from a solid to a gas, that's called sublimation or subliming. You can also go from a gas to a solid as well, and you can do these in different ways. The melting point here is the point at which the solid turns into a liquid or a liquid goes back into a solid. That temperature right there is that point where you would change between these two states. The boiling point is the point where you change between liquid and gas. An endothermic reaction or an endothermic system is one where energy is absorbed. You need to put energy into the system in order for it to happen. An exothermic reaction or system is one where energy is released. Have you ever heard the terms endothermic and exothermic? Endo means inside, exo means outside. Endothermic is where the outside, you need to have something coming, the heat coming from the outside in. Exothermic is where the heat is given off to the outside. Looking at this graph, it is a graph called a heating curve. It shows how the substance changes when you add heat. So we start at point A. As the temperature increases and you're adding heat, so heat added is on the bottom, temperature increases on the side. As the temperature increases and you're adding heat, we're going to go from a solid, and then at the melting point, we're going to turn into a liquid. Now you have to add a lot of heat during melting in order to completely change the solid into a liquid. So that's why this line goes flat for a while. Once you get here to complete liquid, you keep adding heat, the temperature keeps going up, and then you're going to get to the boiling point, the point where you change from a liquid to a gas. Again, you're going to have to add in a lot of heat in order to change all of the liquid into a gas and complete the phase change. And the temperature doesn't change at this point, even though you are adding more heat in. And then you get into the gas stage. For a cooling curve, it's the exact opposite of a heating curve. So we're going to start up here at this high temperature where we have a gas. As we get rid of heat, as we lose heat, the temperature is going to start to go down, and then we're going to reach this point here where we're going to turn from a gas into a liquid. This is the condensation point. This is also our boiling point. So boiling point and condensation point are the same thing. Again, you have to remove a lot of heat in order to completely change the gas into liquid. And then once everything's turned into liquid, then you can start decreasing the temperature will start to go down again as you remove heat, bringing you down to here, which is the melting point, also the freezing point. At this point, we're going to have to keep removing heat, even though the temperature isn't changing, to change all the liquid into a solid. And then from there, you can keep decreasing the temperature and removing heat, even though this is still going to be a solid. That won't change. The phase won't change at that point. So what you need to know for heating and cooling curves is, what does all this mean? What is if I gave you a heating or cooling curve and I said, what's happening right here? What's going on with the substance here? What state is it in? You'd need to be able to tell me that it is a liquid here. Or what process is occurring here? It's freezing, right? So you need to be able to understand these graphs and know what's happening where in the graph itself.